Hi, this is your first tutorial on aldehydes and ketones, and this one is on oxidation and reduction. So first of all, just to remind you of aldehydes and ketones, what the functional group looks like and how they're named. So an aldehyde has a carbonyl group, so that's a carbon double bonded to an oxygen. It has an alkyl chain in one direction coming off this carbon, and in the other direction it has a hydrogen. And to name an aldehyde, you just take the alkane name, take the E off, and put al on the end. So this one down here is propanal, 3 carbons in a row. And a ketone is very similar. It still has a carbonyl group, which is a carbon double bonded to an oxygen. In this direction, it still has an alkyl chain, but here, instead of having a hydrogen, it has another alkyl chain, which might be the same as this one, or it might be different. And to name a ketone, you just put the alkane name without the E and you add ONE, one, onto the end. So this compound is propanone, which is a ketone. This one's propanal, which is an aldehyde. Okay, so when you were looking at alcohols in year 1, you will have looked at oxidation of alcohols and how alcohols can be oxidized to aldehydes or ketones, and the primary alcohols can also be further oxidized to carboxylic acids. So this is just a recap of that more than anything. So looking at the top compound here, we've got an alcohol with the hydroxyl group on the end, so on carbon number 1. So this is a primary alcohol, and this one can be oxidized to an aldehyde. So here we've got propan-1-ol turning into propanal under oxidation. Now this aldehyde can undergo further oxidation, you should remember. So if you want to get the aldehyde off on its own, this is where you'd use distillation. If you want to go direct to the next product, you would use reflux, and that next product is a carboxylic acid. So we've got propan-1-ol going to propanal, going to propanoic acid. So this is oxidation. And obviously from an aldehyde to ketones point of view, we're looking at this step here, which is an aldehyde turning into a carboxylic acid. So next, looking at this compound at the bottom, we've now got an alcohol where the hydroxyl group is connected to one of the central carbons. So this is a secondary alcohol. This is propan-2-ol. And propan-2-ol can be oxidized as well, but this time instead of becoming an aldehyde, it will become a ketone. Okay, and finally, you could try and oxidize this further. However, the ketone can't go any further, can't be oxidized to anything else. So the primary alcohol becomes an aldehyde, which becomes a carboxylic acid. The secondary alcohol becomes a ketone, but the ketone cannot be further oxidized. So it's these bits here that are quite important for aldehyde and ketone chemistry. Aldehydes can be oxidized and ketones can't. And this gives you a really good basis for being able to distinguish between 2 compounds when you know you've got an aldehyde or a ketone, figuring out which one you've got. Now, in terms of oxidizing agents, when you've seen this previously, when you're looking at the alcohols topic, the oxidizing agent you would use to turn this into an aldehyde and this into a carboxylic acid, or to turn this one into a ketone, was acidified potassium dichromate. Okay, so there is the formula for acidified potassium dichromate, and it's the dichromate ion, the Cr2O7 2- ion, that is the oxidizing agent. So as we've put here, it is acidified. This happens under acidic conditions. So the half equation for the aldehyde oxidizing under acidic conditions would be the following. So we've got the aldehyde reacting with water to give a carboxylic acid, 2 protons and 2 electrons. Now looking at the half equation for the dichromate ion. So the dichromate ion is reduced to chromium 3+. There's dichromate and there's chromium 3+. And if you were to carry this out, you would see that the original dichromate ion, which is orange, would turn to green, which is the colour of the chromium 3+ ions. So finally, combining these 2 half equations to give you the overall equation, you get the redox reaction at the bottom. So you've got your aldehydes, your dichromate ions, this is under acidic conditions, so your H+, then you're creating a carboxylic acid, the chromium 3+ ions, which gives you your colour change of orange to green, and some water left over. So the use of acidified potassium dichromate in oxidising an aldehyde and not being able to oxidise a ketone gives you a really good way of distinguishing between aldehydes and ketones, and that's a perfect answer for what chemical you could use to do that. But now we're going to look at a more common one, which is the Tollens reagent. So the tolerance test works in exactly the same way. You have an aldehyde, which can be oxidized by tolerance, and you have a ketone, which cannot be oxidized by tolerance, giving you a positive result for the aldehyde and a negative result for the ketone. Okay, so importantly, you need to know the colour change for this as well. So the aldehyde would give you a silver mirror inside the test tube, and a ketone would give you no change. So to carry out a tolerance test on compounds that you think might be aldehydes or ketones, you first need to make the tolerance reagent fresh. So it is made from silver nitrate solution with a little bit of sodium hydroxide, which forms a brown precipitate. That precipitate is silver oxide, and then you add ammonia solution to redissolve the precipitate. It's a required practical, so you do need to be able to know how you would create the tolerance reagent and then how you would use it. So this complex here, the diamine silver complex, is it's the important part of the tolerance reagent, and this is the part that's going to do the oxidizing. So as it's an oxidizing agent, the diamine silver gets itself reduced, so it gains electrons, and this reduces the silver in the complex down to elemental silver. And it will also produce 2 lots of ammonia. Now, at the same time, the aldehyde, which is the one that will react with tolerance, is oxidized. And this time, because you put the sodium hydroxide in at the beginning, it's oxidized under alkaline conditions. So instead of getting the carboxylic acid product, you get the carboxylate salt. So there's the half equation for that one as well. So we've got the diamine silver, which is produced when you make your tolerance reagent. It's getting reduced to elemental silver, which is what you see on the inside of the test tube, and releasing ammonia. The aldehyde is reacting with the hydroxide ions from the sodium hydroxide, and because this is under alkaline conditions, rather than making the carboxylic acid, it now makes the carboxylate salt, a little bit of water, and the electrons left over, so we can combine them to give the full equation. So there it is. So we've got the diamine silver reacting with the aldehyde and the hydroxide ions from the sodium hydroxide, giving you a silver mirror on the inside of your test tube, a carboxylate salt, ammonia, and water. Now I'm hoping that you're able to do these right in half equations for a redox reaction, combining half equations to produce an overall equation. If this is something that you still think you struggle with, this is an opportunity for us to practice it, so please let me know. Okay, there's also the failings test, which is the alternative to tolerance, and it works in very much the same way, to be honest. So the difference is, instead of having a silver complex, you've now got a copper complex. So where the silver complex was reduced to silver, the copper complex is now reduced to copper oxide. But similar to tolerance, we've still got the sodium hydroxide. So the aldehyde reacts with the OH- ions from the sodium hydroxide in exactly the same way. So the aldehyde is oxidized. Now, again, it's under alkaline conditions, so it's oxidized to the salt of the carboxylic acid. And the copper reacts with hydroxide ions as well to give you the copper oxide precipitate, which you will see as a brick red precipitate. So I'm not going to go through the half equations and the full equations for failings, partly because there's some other complicated ions in there as well as part of the copper complex, but it does work in the same way. But importantly, you do need to know the colour changes for this. So with the aldehyde, the blue failings solution will give you a red precipitate, which is copper oxide, and with the ketone, you don't get any change and it will stay a deep blue colour. Okay, so on to reduction of aldehydes and ketones. So as we've seen at the beginning, primary alcohols can be oxidised to aldehydes and secondary alcohols can be oxidised to ketones. Now this also works backwards, so if you can oxidise that way, you can reduce that way. So an aldehyde will be reduced to a primary alcohol and a ketone will be reduced to a secondary alcohol. And you now know of 3 different oxidizing agents you can use to turn the alcohols into the aldehydes and ketones. So you've got your failings reagent, your tolerance reagent, and your acidified potassium dichromate. So you'll also need to know of a reducing agent that will take this reaction back the other way. So the reducing agent that you need to know about, it's got a pretty horrible name, sodium tetrahydroborate. It's also known as sodium borohydride. So sodium tetrahydroborate is a sodium ion, and then the tetrahydroborate ion, which is the boron in the middle, Tetrahydrido means the 4 hydrogens, and the ion has a negative charge over the lot of it. And this is simplified quite a lot in writing chemical equations to show reduction to just H in square brackets. So H in square brackets means reducing agent, so it can represent sodium tetrahydridoborate. Now, for the purposes of being able to write equations and mechanisms to show reduction of aldehydes and ketones, we are going to stick with that simplified version. But you do need to know the name of this, and this is what it looks like. So to write an equation for reduction of an aldehyde, if we have a little look on the left here, we've got the aldehyde that we're trying to reduce. We know we're going to turn it into an alcohol, so I've drawn the same atoms that we've got here, drawn out in the product, and you can see that to complete this, we're going to need 2 hydrogen atoms to produce the primary alcohol, which is the product. That means that in the reactant, we're going to need 2 hydrogen atoms. So remember, H in square brackets is reducing agent, but it represents an H- ion, or hydride ion, which is coming from the reducing agent, sodium tetrahydridoborate. So we'll need 2 lots of this to react with 1 lot of this to give us this. So that is how we would write the equation. Aldehyde plus 2 lots of the reducing agent gives you a primary alcohol, and we can do the same for ketones. So again, you can see that with the ketone, you're trying to create a secondary alcohol, and we've got the same atoms that are here, rearranged here to start to form an alcohol, but you're clearly going to need a hydrogen there and a hydrogen there to fix it. So we're going to need 2 lots of the reducing agent there to provide those hydride ions, which are going to add on to the alcohol. So these equations you do need to be able to write, but you can write them, and you should write them just using the H in square brackets and not worrying too much about this. The last little thing that you need to know is you need to be able to draw a mechanism for this happening. And again, you can use just the H in square brackets, or the H-, which is what's actually represented, the hydride ion, rather than the whole sodium tetrahydridoborate. Okay, so starting with our aldehyde, first thing we need to do if we're going to show attack of the hydride ion is to look for where our delta plus and delta minus are. So oxygen, being very electronegative, is going to have a partial negative charge on it, and that results in the carbon having a partial positive charge on it. So there's the delta minus and delta plus. Okay, so attacking, we have got H-, this is a hydride ion, and the hydride ion is negatively charged, so it's going to attack our delta positive carbon. Those incoming electrons coming in this way are going to repel electrons in this bond, so these electrons will move up onto the oxygen atom. And this is the result. So we've got the alkyl group, we've got the carbon that was attacked, we've got the oxygen atom, which now has its electrons pushed up onto it, so it has a full negative charge. We have got the hydrogen atom that was already part of the aldehyde, and we've got our new hydrogen atom that came from this hydride ion. So finally, we need an oxygen to add on to here to complete our alcohol, and that can come from water, or it can come from an acid. So if you've got an acid in solution, you will have some protons, and then you will get attack from these electrons sitting on oxygen onto that proton, and your final product will be your primary alcohol. And there you go. So overall, it's not too bad a reaction in terms of a mechanism, because you are simplifying it quite a lot by just using the H-, which is the hydride ion, and H+ coming from an acid. So you don't need to worry about the NaBH4. It would get far too complicated if you were to include that. So I'll show you another mechanism just for ketones, and then we're done. Okay, so this time I'm going to show you with a full ketone, so we're going to use butanone rather than just an R group to represent alkyl chains. It just might be a little bit easier to see and easier to apply to other examples that you've got to complete yourself. So we've got the ketone, and we've also got our hydride ion, which has come from our reducing agent. So first of all, in terms of partial charges, again, your oxygen is electronegative, so that's delta minus, and your carbon has electrons pulled away from it, so it is delta positive. We then get attack of the electrons sitting on the hydride ion. They attack the carbon atom, which is delta positive, so they are attracted to the partial positive charge, and these incoming electrons repel electrons in this carbon-oxygen double bond, So those electrons move up onto oxygen in exactly the same way as before. Okay, so this is our product, and we need to add a H+ ion coming from water or from an acid. So we've got electrons on this oxygen atom. They are going to attract to the positive charge on that hydrogen ion, and that will form your secondary alcohol. Okay, so there you go. There's a mechanism for turning butanone into butan-2-ol. Now, you just need to bear in mind that the reduction mechanisms that I've just shown you, that these are very, very simplified versions of what actually happens. So these are absolutely fine for your exams and are necessary at this stage, because otherwise you'll end up with very, very complicated intermediate products. So learn these using the hydride ion and the H+ ion, and don't worry too much about anything more complicated, including the rest of this reducing agent, because it's not necessary at this stage. So for now, aldehydes and ketones are done. We've still got a little bit more to learn about them in the next tutorial, but that's it for this tutorial. So can you please make sure that you have made a good set of notes in your class notebook, and then can you go and complete the post-tutorial quiz? Thank you.